suppose we have the sample space to some experiment, and let's make it look like this. S sub 1, event 1, S sub 2, second event, S sub 3, the third event, dot, 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 S sub n, the last event. I like to think of probability this way. Imagine you have this one square unit, and I'm going to call that one square unit of probability. So this is going to be one square unit of probability. And then what we're going to do is cut this thing up somehow and distribute it to each one of these individual events. So like maybe what we could do here is cut this thing up so it looks like this. Maybe cut this slice here and take that much and put it here. Let's call that P1. And then we cut maybe this much, P2, and we put it over here with this event. And then maybe this little amount here, P3, and put it here, and dot, dot, dot. We keep cutting it up, P sub n, and we distribute it to each one of these elementary events in the sample space. Here's a really simple example. Suppose you toss a coin once. You could get a head or a tail. There's the sample space. And then if you think of our 1 unit of probability, we're just going to cut it in half here, and I'm going to assign this much to heads, this much to tails. Now if the coin is fair, we kind of have an intuitive idea here. We'll take half and half. Here's another example. Suppose that we have this sample space here, S equals, and in it we've got maybe an A, B, C, and D, and here is our 1 unit of probability, and we're going to cut it up. Maybe I get a little bit right here. I'll call it P1, and I put that to the A, right? So I'm saying this. I'm saying that the probability that A occurs is this number right here, P1, whatever it is, 0.2 or whatever. And then maybe B might be this much right here, P2, percentage 2. That goes to B. The probability that B occurs is going to be this number right here. And then the probability that C occurs is maybe this amount right here. Maybe that's P3, that would be the probability for C, and then P4, that would be the amount for D. So we're going to just talk about probability distributions. Now here's one way to write one. What I want to do is display a probability distribution. I could do it just like this over here. Right, I could write out the sample space and then draw this rectangle and then cut it up like this. It's a little inconvenient, but that's a legitimate probability distribution. Now another way to write a distribution is to write this. Here's S, here's P, and then you could write, okay, here's the outcomes, S1, S2, dot, 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 S sub n, P1, P2, dot, 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 P sub n. Okay, so you could make a table. This is a perfectly good way to display a probability distribution. Outcome, probability of that outcome. And then maybe here's another way that can be useful. I might say the probability that S equals S1 is P1. So I might read it like this. This is the probability that the outcome is this particular one right here. That would be P1. And then I could write the probability that S, the outcome, is this particular one, S sub 2, that would be P sub 2, where S is the outcome, and this is a particular outcome. So I would read this, the probability that the outcome is S2 is P2. And then I just keep on going, right, dot, dot, dot. The probability that the outcome is, say, that last one, is P sub n. So these are all ways of displaying a probability distribution. So let's suppose that you have some experiment with these particular outcomes, all right, these individual outcomes. Maybe it's rolling the die, right? So what could the outcomes be? A 1, 2, 3, 4, 5, 6. And then we have this distribution, right? We're going to display how we're going to distribute this. Here's the outcome. Here's the probability of that outcome. Here's the individual outcomes. Maybe it's a roll a die, 1, 2, 3, 4, 5, 6, and the corresponding probabilities. So suppose you've got some distribution like this over here, but with actual numbers for probabilities, and you want that distribution to be a valid probability distribution. So if it's going to be valid probability distribution, it's got to satisfy both of these conditions. The first one is this. For each S, right, so for each individual outcome, right, so for each one of these, these numbers here have to be between 0 and 1. So what we have is this. For each one of those S's, this has to be true. 0 less than or equal to P less than or equal to 1. Right? Because they're probabilities. So they have to be between 0 and 1. Let's make that clear. You know, I like to think of it this way. Here's my 1 unit of probability. Right? That's 1 unit of probability. And if I start splitting it up, right, this amount here, I got 1 unit. That amount here is going to be bigger than 0, but less than 1. And that's what I mean by this. So for each one of these S's, for each S, that P, the corresponding P, for that S, this P has to be between 0 and 1, right, because it's one of these. So that has to be true. For each one of the S's, the corresponding number that you put here has to be between 0 and 1. And the second thing that has to happen is that P1 plus P2 plus ... plus P sub n, that has to equal 1. Maybe that makes sense if you look at cutting this thing up, right? Here's some number between 0 and 1. You cut it up again, cut it up again, cut it up again, cut it up again. If you put all those cuts together, if it's a valid probability distribution, you've got to get back to that whole square unit of probability. And we have a shortcut notation for this. You've probably seen this before when you did sequences and series. If you add up a bunch of numbers, you write a sigma. Sigma is a Greek letter, starts with S. So does sum, so that's why we use it. I'm going to add up the p's, and I should get 1. So if you write a distribution, it's going to be a valid probability distribution if both of these are satisfied. And if I'm given a distribution and want to prove to you that it's a valid distribution, I have to discuss each one of these. We can look at an example here. Here's a distribution. So the outcomes, some experiment, the outcomes are A, B, and C. And here's the corresponding probabilities. But I've written a distribution. Is it a valid probability distribution? Well, if it's going to be valid, I have to show both of these. So I really have to talk about both of these. Here's how we do it. So I'm going to say this. Number one, by observation, that means I've looked at this, I've looked over here, and I'm convinced, by observation, I'm convinced that for each S, this is true. 0 less than or equal to P less than or equal to 1. Do you believe it? By observing this, you can see each one of the corresponding P's is between some number between 0 and 1. And the second thing that happens is if I add up the P's, I get exactly 1. Right? What do you get? A fourth is a half, plus a half, you get 1. So what I'm saying is that I've got both of these described. I can't just say one of them without saying the other. I can't just say, oh, the sum of the P's is 1. I have to actually present to you both conditions. Here's another example. You see this one here? We're saying that the probability of X is a 2, and the probability of Y is a -1. This isn't going to work, right? But be careful. What if you just look at this condition here? What if you just add up the probabilities? If you just added up the probabilities, you would get 1 and think, oh, that's a legitimate distribution. But it's not, right? Because number one, you would say by observation, abbreviate, by observation, it is not the case that for each S, 0 less than or equal to P less than or equal to 1. So condition 1 fails. So condition 1 fails, and as long as one of them fails, I can just claim this. This distribution is not a probability distribution. Let's go on and do some problems now out of the homework set.